thanks for your patience with technological stuff. Thanks for the invitation. I feel something like the odd person out, the lost son in some way. That's why I entitled it was a journey. So it started here, and today I'm back, and this is wonderful. So I'm in Royal Holloway. Do I have a mouse? Yes, I have a mouse. This is, no, yeah. I was told this is my office. It's not true. Oh, sorry, yes, I can, yeah, super. It's definitely not true, but actually it is 200 meters from my office, and it's a compact university. It's a campus university, and it has some very odd parts. To switch on. Ah, das ist hier. Ja, das war gut. Ja. Nee, it's okay. Ich kann noch. Ja. Sorry. So it's a folly in itself, the university, and it has in the last 20, 30 years achieved quite a bit of reputation, in particular for neuroscience, because in the psychology department we had a strategy to bring neuroscience into something which was quite old-fashioned. And I'm there since 2000, but I was here in 81. And I think the reason why I accepted to talk about this is because I wanted to talk about what is so special about the Max Planck Institute. And there are certain things which are absolutely unique and which they allowed me to come into many different fields and coming back as well, and doing things which nobody would have expected. So the starting point is Tübingen, and I still don't know where to press. Forward. I'll do it from here. Yeah. So I started at the biology department of the university, and this is the first wonderful point here. There was a very strong connection between university and Max Planck. And during the final years of an undergraduate study, there was a thing which was called Großpraktikum, and it is a full term or full year of lab work, which was done with enormous creativity. You could design your own experiments, and you had experts coming to the lab and teaching you. And this is how I made my first contacts to the Max Planck Institute. There were two young scientists, Christian Werner and Klaus Hausen, who did experiments on flies, something which we as students never had heard before. But we had this opportunity in the Cybernetics department at the university to learn about this under the overall control of Dejeu Vayu, who was mentioned in the morning, which was a good friend of the people at Max Planck. And this strong connection was something we could benefit massively from. And that's what we did. So with Christian, we did an experiment about landing a response in flies. And for some reason, he invited me later to come to the Max Planck Institute and to run a summer project in it as an undergraduate student. And I was allowed to or build my own setup. I was about to build my own procedures, of course, with guidance from the people in the Max Planck Institute. But I was feeling quite strongly in charge of this project. And what we did try to understand was the landing response of flies, in particular, which visual stimuli were leading to this very typical stereotypical response of flies. And at the end, we found out by having tethered flies hanging in front of the monitor and blinding on one side, that the preferred responses were clearly organized in an expanding circle of the visual system. This then related back to what we had learned in the theoretical parts of this course, for instance, about the theory of direct perception, for which optic flow and optic flow patterns were essential. So basically, we had this wonderful opportunity to combine literature, which is contemporary with almost contemporary or recent theoretical frameworks and practical work. And this was in some way unique. And we were given time to do that. And in this case, I had this extra round in the Max Planck Institute, which even led to my first publication as an undergraduate student. So this is why one point why Max Planck was so amazing and unique. This little project was followed up by a lot of proper, serious, in-depth research, like free flight landing responses by Hammer Wagner, and Axel turned up and did some experiments on the time codes of landing responses. And I just looked when I prepared the talk, are people still interested? Yes, there is a paper in 2019 still working on this particular question of animal flight. So this was the start for me. But I wanted to know whether things are different in different countries and different departments. And there was in the insect flight or insect vision community creative dispute between Tübingen and Sussex, where they had different ideas about this. So it was absolutely logical for me. I have to go there and learn from them. I could do that. And I went to do my master's course or my master's project in Sussex. At the end, because they were very creative and they were sort of developing ideas out of the nothing, I was working on something different because I also had to learn that there are insects which don't fly, not only fly, but also walk. And we got closer to these creatures, ladybirds, which are very interesting because they are walking on the ground, not flying in the air. And they can use proprioceptive information to control their locomotion. And this is an added new component of understanding how insects operate in environments. We did experiments in the lab. This was together with Tom Collett. We were catching ladybirds on the local golf course and put them on little ridges and let them walk on a ridge. And as you can see from here, this is what ladybirds do. They walk on the ridge and fall down at the end or start flying away. This is what inspired this. Yeah. But we also, of course, did the typical Tübingen thing. They were walking on a platform and inside a drum, which rotated. And we looked at the optomotor response of freely walking ladybirds. But most interesting was this experiment on a predefined path, because these insects are very, very robust in just walking on a line whenever they see it. So one of the things was trying to understand this, these responses coming not from visual input, but from input in the proprioceptive system. And obviously what you do is you let them walk on horizontal paths, ascending paths, horizontal paths, and way back. Right? And they do this nicely, and then you can look at the speed and you get a curve of speed in relation to angle. And if you're really nasty to the animals, you let them pull little weights and see how the speed changes with extra payload and whether they control this or not. Yeah? Again, the results, I don't need to go through all of this, but this is the approach. This is the broadening of ideas from a small area into many different things which you could do. And yes, again, this could be published, although it was a very rough and ready experiment. Without the splendor of the Max Planck Institute workshop behind it. From there, I went back to Tübingen, right? Because I thought, okay, now I'm ready for Tübingen and can see what I can really learn from them and where the different strengths can be combined. And I ended up with a PhD in the lab of Carl Goetz, which was rather tricky project. And again, it was a choice by myself in some way, because I was interested to understand before we can understand flight control, we need to know how they can fly. And this turned out to be a rather tricky problem, because in particular, the small flies, Drosophila, actually don't fly, because the physics conditions in a very highly viscous medium, being very small, means that they cannot use standard flight mechanisms which rely on laminar flow. And without laminar conditions, you can't really fly, and you need to think about something different. The evolution did. And there is a quite well developed theory of turbulent flow. And the important thing is that you have a Reynolds number in the medium in which you are, which tells you what you can do and what you can't do. And it's absolutely clear that flies can't fly with conventional aerodynamics. So I was lucky enough to have Carl Goetz as my PhD supervisor, because he was a physicist and a very, very smart physicist who really knew what it is, and also gave me the freedom to explore things myself and and experienced the frustration when I came up with a wonderful idea, and he opened his drawer, pulled out a manuscript and says, yes, I have written this up 5 years ago, but didn't have the time to publish, right? That was a typical thing for him, right? He knew it, but he not necessarily thought he needs to talk about it. So, another thing which I definitely need to say, the workshop. So this was the work which I did in this project involved the workshop a lot. And Max Planck had this wonderful workshop with the workshop leader Heile Braun, who became a friend of mine because I went so often into the workshop and said, oh, can you help me with this? And can I do that? And at the end, he allowed me to use the tools. Directors didn't know that I was doing this. And to build some equipment to measure things which I need for this project. So this is the first part of what I needed. So as we all know, these Drosophila are very small. They fly at, let's say, roughly 200 hertz, wing beat cycles per second. So you need a high-speed camera, which goes into a very small area and want to understand how the wing moves in a single cycle. So it needs to be fast, highly precise, and so on and so forth. Obviously, that was far out of what you could get as in the commercial sector. So the workaround was to use a conventional camera, which can be triggered electronically. It was just a normal cannon. The cannon was triggered by a device which picked up the movements of the tiny little movements of the fly, or forces of the fly, at 600 hertz, and then divided that by 50. So I knew exactly at any time at which phase of the cycle the animal was, and just needed to have an electronic device to run through that. So I had slow motion pictures of the animal flight. In addition, it should be from several different angles because we wanted to reconstruct the wing movement in 3D, and that took me about a half a year to build, test, and finally I could come to the office of Carl Goetz and tell him that I did something, and he was very happy, I think, and it was good. Yeah? So with these photographs, we could map the wing, or both wings, on a 3D spherical space, and for the left and the right eye, and the spherical space is shown here as a globe with its coordinates, and we now could have a full description of the wing beat cycle of Drosophila. And this is sort of a non-animated version of it. And you can see a lot of this is what you see is completely different from airplane flying stretched out wings, or even helicopters have much less complicated patterns of flight. So, and this is after the triumph of finally understanding how they fly, came the shock of trying to understand where the aerodynamic forces come from. And that means, oh yes, oh sorry, that was, so with the, with these reconstructions, I also could create actual movies, slow motion movies of what they're doing in high speed. And I had my 3D cinema in the lab where people could watch flies flying in slow motion. And this is an example of how it looked like. And I just show this for sentimental reasons, not because I still had a white beard. No, a black beard, actually. It was in the room below Werner Reichardt's office. There was a tiny little lab in which I could squeeze this, my office and my lab, and have visitors here from overseas. Here you can see, oh, I can't see that. Yeah, somewhere there, this little thing, this is the setup. And that is sitting in the center of this apparatus. Yeah? And yes, for me, it was the fun of science. It was really joyful to do that and trying to work out. Now, the aerodynamics is a dynamic is a dynamic in true sense, because for each cycle it changed the forces and velocities changed with 200 hertz. So I needed to measure these forces. For that, I built a kind of what we would call an interferometer by putting the fly on a string, which was sort of checked with a laser beam how much it was moving up and down. And you can imagine the string was moving in minute quantities, but from the interference of the laser beam, we could work out how much it went up and down and calculate from there what the forces are. And then we had the full aerodynamics, which I don't go into detail now, and compared the aerodynamics on the kinematics of this. And then I was very happy, was writing for almost 2 years on this. And I don't know whether you remember the day when I came to the Max Planck kitchen, to the desk at lunchtime, and was complaining again that I had 2 years of pain for this, and nobody wanted to read it because it was published by the Philosophical Transactions. But at that time, you got inquiries from colleagues to send a copy of your work, and never got anything. And was super frustrated. And I came back to lunch and said, "Oh God, another day, and nobody's interested." And then Martin, who should be here and talk instead of me, he said to me, "Have you seen Nature today?" I said, "No, why?" And he said, "Oh, there was a commentary on your work." And I thought that is good enough. And this is the cartoon which they put in about the movements of the wings in flies. And yes, so for a day or two, I was happy. Yeah? All of this I left behind, not because of the frustration of not being cited. Has changed, by the way. But because I was thinking already about other things after doing this, right? And sorry, that was and the work itself was continued by people who were much more competent in doing this. Michael Dickerson, I think a couple of people who know him are here. He followed in the lab with a super clever technique by putting little objects into a fluid, so we could see exactly the streams, the non-steady streams of airflow in a model of the fly, and so on and so forth. And this is also going on and still continuing. It all started in a basement lab of Max Planck Institute, right? Where not the sort of the price of the equipment was important, but the ideas of those who came together to do some science. Right? Okay. My ideas already started to go into other areas. I thought, yeah, actually, the Max Planck Institute is or the department for I was interested in motion vision. There was the world-dominating Reichardt detector, and this is, of course, a challenge to think about Reichardt detector in the way. So, what can't the Reichardt detector do? Because at that stage, it was almost like you can do anything with the Reichardt detector. And I came up with some crazy things, like if this is a space, a space-time, space-time diagram of random dot pixels. So in the background, they are randomly. There's nothing to see, it's just noise. But in a particular region, in one area, you have a pattern which is moving over time to the right. And if without the background, you would think it's moving to the right, but it's constructed that the texture on top of this area is moving left, while the region in which it moves is moving right. And I call this a paradoxical stimulus. And actually, at the beginning, we didn't know how it looks until I made it, and yes, it does work. Oh, sorry. Yeah. So it does work. So you have a region. This is now in color code. You have a region which is colored red, which where's the map here somewhere? It's colored red, which corresponds to moving left, but the region itself in which the dots are moving left is moving right. But you can do psychophysical experiments where you ask people, so where is it moving? And they say right, although everything is moving left. And in order to sort of bring this together with Reichardt model, I just needed to have a second level of a Reichardt network and have the motion of the motion being detected. And this is what I think the next slide shows. So if we build a hierarchical model of Reichardt detectors, here are the first level Reichardt detectors, which look at the components, the little dots, and then we look at where are these motion responses going. Is detected in a second level. So all of this suddenly becomes clear, and we have a perception of object motion in the right direction over a long range of possible velocities and different dot sizes. And it's clearly visible. So these are psychophysical data. It's clearly visible by any naive observer. And luckily enough, it was also detected by the Reichardt detector if you construct in a two-level system. Now, having done that, I thought, okay, that's time to leave. I wanted to go to London because I wanted to learn psychophysics, proper psychophysics. for me, it was just everything was from textbooks. I didn't do proper psychophysics before. But and I had made contacts to Oliver Braddock in London, so he said, "Yes, come, we do work together." But then on one day, Werner Reichardt came to my office and said, "Listen, I heard you're doing strange things here," and I said, "Yes, I have the stimulus, and I think it's perceived in an unconventional way, and I think I have a solution how to get a model for it." And he said to me, "Oh, why don't you do this here?" And he gave me 2 years postdoc in Max Planck just for this crazy idea. And we tested it in flies, right? So because the human error is not possible. So this is the stimulus on a monitor, and this is the standard recording from this is Califora, yes, presumably. And the stimulus is moving right, left, and we look at the responses. And yes, of course, I was confident about that. The fly can see the object movement, yeah, which you can see here, but also conventional Fourier movement. Now, in the naming, there's still a bit of confusion because everybody calls it differently. Because in the Anglo-Saxon regions, they were using other words like what I would call first and second order motion. They would call differently, and we agreed at the end about first and second order. And yes, also for some time I call it theta motion, but you don't need to know about this. This is just the areas which are. So in 1994, so this is some 13 years after I started in Tübingen in the Großpraktikum, I finally got away and went to in a very positive sense. I got away, right? I could come to my next step of my journey, of my exploration of how we do science, right? And tried to learn psychophysics. Oliver Braddock at that time was no longer in Cambridge, he was in London, so I had to move to London. But it was a wonderful time. And it was cut short a little bit to 2 years. I had lots of possibilities of collaborations. Lots of experimental was done, little was written. And the best thing was I had conversations. So with Oliver, I went into a lot amount of many different labs in London with different ideas. And it was crazy because London was beaming of people who knew psychophysics, were super clever and could bring me on the way. This is just one particular experiment, which I don't talk about. This is again about movement, yeah? And I was still sort of fascinated by the EMD, the Reichardt detector, and was basically in England treated as the representation of the Reichardt detector, and they challenged me on many ways, and I enjoyed that. In 2 years later, I got a call from Australia, and they wanted me to come to the Australian National University in Canberra, because they were interested in the combination of psychophysics and insect behavior. And they thought I could be the right person. So after some conversations with family, we decided, yes, we go, and packed everything and we went down under. It was an institute where there was a wonderful combination between biology, engineering, and modeling. And there were extremely accomplished people in all these fields, and we had lots of interactions and conversations, which brought me intellectually forward. But one thing, which I will definitely never forget, is fieldwork. I was doing fieldwork there because, yes, in Australia, you have a lot of empty space with increasingly scary animals. And I was working during that time with Johannes Zanker, who also, by the way, came from Tübingen. And we started with something with recordings which he had made on the beach in Kuwait of fiddler crabs. And they have particular ways of communicating with each other with their claws and body movements. And our very unmodest interest was to decipher their language by looking at the motion signals. So, and I show this here because the starting point for us was to code to transfer the movies. So these are stills from movies into motion patterns. And the motion patterns are sort of color coded. So they are horizontal, vertical coded. So everybody can immediately see what's going on. And you can see how rich the communication between this crab here in the front and another crab in the background is. Again, this was a great step forward, but then the real work has to begin, and the financial support for that wasn't really there. Yeah? So at the same time, I was in the lab working on these funny motion stimuli. This is a comparison of objects moving, which are defined by luminance, Fourier motion, or theta motion. And you can see that the preferred direction of this was looking at the direction of motion in this, right? Is clearly matched for the standard Fourier stimuli, but for these theta motion or paradoxical motion stimuli, you have typical and characteristic deviations, which then again can lead to not a non-formal model, but for design for a model, how you can create exactly these responses. Yes. And going outdoors was the real advantage which I had. Again, with Johannes Zanker, we were looking at ants. This is the jumpy, the jack jumper. And can you see the weapons at the front of the, when you get bitten by one of those, you're lying on the floor and crying for an hour. So we had to work very carefully with this. So they have a wonderful behavior. They have built nests. They go on harvesting trips and come back. And the harvesting trip can be random or quasi-random, and then they go on the direct path back. Right. So this is a typical task for for an intelligent system. So here you can see Jochen putting up the camera to map the terrain in 3D. So we built a panoramic camera to do that. And then you can see here are the nests of these ants, the ants, and yes, these were the kinds of mistakes I was not allowed to do in Australia. Yeah. I'm saying, oh my God. That's why I usually refer to the animals. So they were, these were the, oh, come on. Here you go. So in the center, you have the position of the nest. Yeah. I lost that. Yeah. This is the nest position, and they could be at different points. Then they go out for harvesting and come back straight ahead. Right? And what we did is, because that could not be done by any optomotor responses, so they needed to have a map of the surrounding. But the map has to be created from their visual system, which was some way a very clever camera. So we transferred the pictures of each of these positions into a panoramic map, and then traced the panoramic maps on the way back, and found, first of all, that there was always one point where you have a minimum difference between the current map and the final position which you want to land at. And that was basically the antenna to which they have to walk back. So it was quite interesting, nice. And whilst this would solve their problem, it still could be computationally very expensive, but they only have a small number of ommatidia in each of the eyes. So we tried to work out here how small and diverse we can make the pixels for each of these 360 degrees and height positions that you need, and minimize that. And we're amazed to see that with 100 pixels, they could solve the task. So my new interest was arts, and for a reason which I can explain as well, but that would take longer. And what's most obvious is there are artists who paint illusions, motion illusions. So this is a fixed painting. If you start looking at it, it starts moving everywhere, right? But it is not, right? This is very pretty clear to me. It's the eye movements which we make, which create incoherent optical shifts. The scientific community wouldn't agree on this, but that comes later when I was back in London. I just want to say that in Australia, traditional Aboriginal groups have patterns which look exactly like Richard Riley paintings, right? So in some way, they have an intuitive understanding of this motion illusion as well. Difficult to communicate. So this is now was in my fifth year in Australia, and I got this feeling that there is this. I don't know whether you ever feel that this fear of diffusion, the horror of diffusion, that you diffusion away and into all directions and don't know really where to go, right? And this is what I had. But I also, we had the problem that at that point, our oldest daughter went to university in Europe, and that is on the other side, right? So suddenly our family would have been disrupted, and we thought, okay, at some point we need to go back to Europe, and that was the call to Royal Holloway. Yeah? And Royal Holloway you saw it, right? It can look very attractive. They had a good environment. They had a strong interest in neuroscience. They were the first department in the UK psychology department with independent independent imaging device, and we still have it. It will be replaced now with a new scanner and this year. I had a continuing interest in motion perception, motion combination. This is just something which a PhD student did who had a stronger interest in computational modeling than I had myself. So he was clearly contributing a lot to this. And there was this steady interest in these motion illusions. Not sure whether at that distance everybody can see that. That is a painting by Kitaoka, a scientist and artist from Kyoto. Can you see how they start rotating when you look at them? Yeah? That's the rotating snake's illusion. And his most famous piece of work is he created a CD cover for, oh God, who was the artist? One of the Lady Gaga, I think. For Lady Gaga, he created a CD cover. This is his most cited paper. And there are lots of those, right? And I started working on creating them myself, not exactly these, but trying to find the understanding mechanisms. Closer to us as biology is this painting by Victor Vasarely. It's related to the idea of motion dazzle, which was promoted in the First World War by painting ships in ways which make them difficult to find, disappear, and track. Very problematic assumption. A counting exercise of sunk ship did not leave significant results. So it's questionable. But you have seen a zebra before, right? What does a zebra do? The zebra moves. Can you see individual zebras in the movie? No, you can't. You can move that. The whole herd is moving in the same direction. But imagine yourself when you're a predator, want to get one zebra. You will be constantly distracted by another zebra somewhere else. So down here, you have the 2DMD model. This is again the model, the motion Reichardt detector model with different directions showing patterns of different directions as colors. And you can see how confusing this is. Right? There is no clear answer where it's going. 2 minutes, right? Yeah. Okay, 1 minute is about the interest in eye tracking, because eye tracking gives us a clear understanding of what's going on in the brain and how motion processing is used in various brain functions. This is Mike Land from Sussex with his first home-built eye tracker, mobile eye tracker. So there's a computer in here, there's a camera and an extra monitor here, and he is making tea. And this was a sensational piece of work that we could see where we are looking when we are making tea, and there's a lot of predictive activity in the tea making facility. This is just from one of my mobile eye trackers which I use in teaching. You can see the differences now. They just have a set of glasses and a mobile phone in the back pocket. And that was a study to see where do people step when they walk up or down a staircase, and where do they look when they do that, right? And actually it is basically, this is giving us the target where we want to go, and then we put the foot on there. So this is the strategy of not falling off the staircase. We can do optic flow now in natural environments as well. With these glasses, it's very simple. And Sonia Durant looked at the corrections which we make with small eye movements to stabilize our eyes when we are going through an environment. This is a completely different project. It's a gaze-driven evolutionary algorithm. So here we have properties of objects coded, and then at the beginning, you start with a random position, yeah, and go through just evolutionary algorithm, which is driven by amount of time you spend on looking at it. And at the end, you get your favorite design. In this case, it's the golden section. In this case, it is a Pringles package, which was a dummy Pringles package. We had to do that because the project was funded by Procter & Gamble. And that was the output which they wanted. And at the end, they didn't even ask for the patent. So everybody can do it. Yeah? This is eye tracking in the museum. Jackson Pollock painting. On the top, you can see the fixation maps, heat maps. And on the bottom, you could see how with increasing fixations, the areas are drawn out, which we prefer to look. And none of us, including myself, who had seen this painting 50 times or so, have ever seen that there's a little face drawn at that position. Right? So it goes completely unnoticed. Only through this eye tracking analysis, we have an idea what is going on. And this is the final thing is our Mondrian project. In Dresden, there was a reconstruction of a Mondrian design which was never built. It was designed for a room in Dresden, and we went with virtual reality reconstruction of the room, which was never been, to the Dresden Museum, and had people looking inside what they, are they? What they are interested in. So they're coming outside, and now they go in, and this is his model. And we can see what they were interested in. And it gives us an answer why it was never built, because it wasn't good. Yeah, so that is the picture -1. You don't want to see this. This is our latest VR project. It's the reconstruction of a chapel in Rome, which is usually in dark, closed up, and we were allowed to do a VR reconstruction for that, and now have it sitting in our lab, and you can go and look around and find things, and you can see, for instance, these illusions along the walls. And that brings me to the end. I just want to thank the organizers, in particular for the patience of my failures here. Some range of organizations which are supporting us. The colleagues and friends, which were still talking with me and trying to work out my ideas and support me. Of course, Werner Reichardt, because here it is where it all started. And then I have to thank my family that they're putting up with me. And I asked them whether I can show a picture of them. And yes, there is the picture of the family, right? This is the second generation. These are our grandchildren. So, yeah. So you can see there are competing interests in this, and I'm happy that I'm allowed to do some work from time to time and come here. Right? Thank you very much.